Hello everyone, welcome to the Analog Communication Engineering playlist. Here in this session, I am going to explain about modulation index in amplitude modulation. Now, in previous session, I have already explained you what is amplitude modulation, and based on that, we have derived the mathematical expression of AM signal. Now, in the AM signal expression, if you have remember that the expression was SAMT is equal to AC into 1 plus K cos 2 pi FMT bracket into cos 2 pi FCT. That means here K is denoted as modulation index, where AM cos 2 pi FMT is my message signal and AC cos 2 pi FCT my carrier signal. Then modulation index can be defined as it is the maximum amplitude of modulating signal by the maximum amplitude of carrier signal. That means the modulation index can measure the extent to which carrier voltage is varied by the modulation signal. When K is equal to 0, no modulation, then K is equal to 100 modulation and K is equal to 1 over modulation. Now under, over and perfect modulation, I will explain later one by one. So now in this slide we can see that what is modulation index. It is basically the ratio of maximum amplitude of message signal or modulating signal divided by maximum amplitude of carrier signal. So the amplitude of modulated signal SAMT is equal to, as I derived it in previous session, that we can write it A plus MT cos omega CT. Here A plus MT known as envelope of the modulated signal. Remember that A plus MT known as envelope of the modulated signal. That may be regarded as the carrier signal cos omega ct whose amplitude is given by A plus mt, that means the DC signal. Okay. Now, if passage plus DC, that means A plus mt, is positive, then the envelope of the modulated signal is the same as the message, and the demodulation can be carried out by the detection of the envelope of the carrier, where envelope is, again I am saying, A plus mt. Envelope means A plus mt. Okay. Now, condition of distortion-less modulation, always remember that is A plus mt greater than is equal to 0. That means A plus mt max. What is mt max? Mt max is the amplitude, maximum amplitude of message signal, and what is A? That is the maximum amplitude of carrier signal. So, if above condition is not satisfied, then mt can be recovered by the envelope detection. It can be, okay, it cannot be, but we can still coherent detection method. Every envelope detection, coherent detection, I will explain you session by session. Okay. So modulation index M is equal to, we can write it mt max by A, where A is, again I am saying, where A denotes the maximum amplitude of carrier signal, and mt max, obviously we know that mt max is the maximum amplitude of message signal. So if mt max less than is equal to, that means mt max less than equal to A, that means the carrier signal less than carrier signal. Okay, then it is carrier signal, then it is mt is A less than 1. When m less than 1, then mt max less than 1 or less than A. Okay, and that envelope is not reaching the zero amplitude axis of the A mode. Remember, when m less than 1, that means the amplitude of message signal less than the amplitude of carrier signal, then the envelope, AM envelope, already I have defined you in the previous classes. Laterly I show you, that means this. Okay, so this condition, when A greater than mt max, when this condition is satisfied, that means this envelope, A plus mt envelope, cannot touch the axis. Okay, A plus envelope, this the envelope is not reaching the zero amplitude axis here. Okay, Now when m is equal to 1, these are the conditions. First condition, m less than 1. Okay, that means the maximum message signal amplitude must be less than maximum carrier signal amplitude. Now second is m is equal to 1. This is known as under modulation. This condition number 1 is known as under modulation. Now condition 2, when m is equal to 1, then mt max, that means the maximum amplitude of message signal or modulating signal, is equal to the maximum amplitude of carrier signal. Then the small variation in the magnitude mt will cause the envelope distortion, maybe but may not be. Okay, waveform envelope just touch the zero amplitude axis. That means it will happen in this manner. Here, this is the waveform of modulation index 1. If modulation index 1, then the waveform, signal waveform, touch the zero amplitude axis. Okay, and last condition is this: when modulation index is greater than 1. If modulation index greater than 1, that means the maximum amplitude of modulating signal greater than to the maximum amplitude of carrier signal. If this condition happen, then this is known as overmodulation. And when overmodulation happen, then always remember, envelope detector can't extract my original message signal back. Okay, that means this thing will happen. If modulation signal is greater than 1, then this thing will happen. This is the cross of overmodulation. Okay, there is a overmodulation where the distortion is happening. This is the distortion section. So this is actually the significance of modulation index, we can say. In modulation index, that means defines that how my modulation actually occurs. Is it under modulation, is it over modulation, or is it the perfect modulation? Again I am repeating, under modulation, when modulation index is less than 1, that means Vmax minus Vmin, that means modulating signal by maximum amplitude of modulating signal or maximum amplitude carrier signal less than 1. Perfect modulation happens when m is equal to 1, modulation index is equal to 1, and over modulation happens when modulation index is greater than s. Always remember, we never prefer over modulation. Okay, so these are the modulation where a is greater than mt, and the next figure is a is less than mt. That will over modulation happen, and whenever the over modulation happen, then this crossover section happen, and there is a phase change. Okay, there is a phase change happen. So significance of modulation index, in a short we can say, m is merely defined as a parameter which determines the amount of modulation. Okay, always remember, we prefer modulation index less than 1. The ideal condition is m is equal to 1. This is important to focus the retrieval of the original message signal. Now this is the Matlab code. Okay, this is the Matlab code of the different amplitude modulation, that means the under modulation, over modulation, and perfect modulation. Okay, so you can go through it, I can explain it. Suppose the first condition is the display, then I prefer the input. Here I the first condition, m is equal to 1, that means the 100% modulation or perfect modulation. Okay, now first I modulating signal, first I generate the modulating signal. So I fix the amplitude of modulating signal, m is equal to 5. Then I fix the frequency of modulating signal, fa is equal to 2000. Then obviously the time period of modulation signal and total time for simulation. Then I write the expression of modulating signal. Okay, then figure 1, obviously the plotting, then figure 1 in under it I plot a subplot. These figures, modulation 1, 2, 3, modulating signal, then the carrier signal, and then the modulated signal will happen. Okay, so first it will plot the modulating signal, then I generate carrier signal. So carrier signal AC, I generate m by m. Okay, then FC, I take the frequency of carrier signal, time period, I generate the signal, and I plot the carrier signal. Lastly, the AM modulated signal. We know the mathematical expression of modulated signal. I have already derived it in previous session. So y is equal to AC into 1 plus modulation index into my message signal, bracket close, double bracket, into the carrier signal. This is the modulated signal equation, and it will plot in this way. So if I change the modulation index here, the first figure I draw where m is equal to 1. Now if I make m less than 1, that was 0.5, then we will get the figure, and if I make m is equal to greater than 1, then we will get the overmodulated waveform. So this is the waveform for modulation index 1, this type, okay, where again I am saying the envelope of the modulation index touch the 0 amplitude axis. If modulation index is 0.5, then this kind of waveform, that means this is the under modulation, this is perfect modulation, the 100% modulation, okay. So where the envelope does not touch the 0 amplitude axis, and this is the over modulation, the modulation index I consider is 2, so obviously the crossover section will happen, and over modulation where I cannot retrieve my message signal back using a simple envelope detector. So we never prefer over modulation, okay. Now the modulation index that we actually use in experimental, okay, so it is very interesting, try to understand. So I have drawn a AM wave using under modulation, okay. So maximum M is equal to, we know, so here the maximum, here the EM is the modulating, maximum modulating signal amplitude, and EC is the maximum carrier signal amplitude. So M is equal to, we know, EM by EC, right? Maximum message signal amplitude or modulating signal amplitude divided by maximum carrier signal amplitude. So EM is nothing but half of Emax minus Emin. What is Emax? This entire here, this arrow actually explains the Emax. That means from 0 amplitude axis to the maximum amplitude, that is Emax, okay. And minimum is the 0 amplitude axis to the minimum, where the minimum envelope, okay, that is Emin. So EM, that means this part, is obviously the total Emax minus Emin, half of, okay. Current if Emax minus Emin, it will do 2 EM. So EM is half of Emax minus Emin. Hope it is clear to you. It is very simple. Now what is EC? EC is nothing but Emin, that is this part, plus EM, isn't it? Emin plus EM. Already I have had EM. So Emin, that means this part, plus EM. So Emin plus EM is the EC. So that means Emin plus replace EM is equal to half of Emax minus Emin, what already we have tried. So from there we will get EC is equal to half of Emax plus Emin. Now we know the modulation index formula, that is EM by EC. Put EM, replace EM with half of Emax minus Emin, and put replace EC with half of Emax plus Emin. So half of get cancelled. So modulation index can also be defined as maximum the envelope, that means Emax minus the minimum envelope Emin by maximum envelope Emax plus minimum envelope Emin. This is the another modulation index formula that is used to solve numerical, and when we want to extract modulation index from the experimental setup, that means the oscilloscope waveform, so we use this formula, okay. So hope it is clear to you. Therefore this many things we need to understand for modulation index, okay. Thank you so much for watching this video. In the next section I will be going to discuss about the AM transmission power. Thank you again for watching this video.